Onda UNED. Imagen y sonido, hasta donde estés. Un espacio de la Escuela de Ciencias Sociales y Humanidades de la UNED. Hasta donde estés. Onda UNED. Acortando distancias.
Buenos días. En nombre de la Benemérita Universidad Estatal a Distancia, les damos la más cordial bienvenida a la apertura de la celebración del Día Internacional de las Telecomunicaciones 2021. En el marco de esta celebración, se realizará un ciclo de conferencias virtuales y gratuitas que se impartirán durante toda la semana a partir de hoy y hasta el 20 de mayo. La actividad del día de hoy es organizada por el Programa de Ingeniería en Telecomunicaciones de la Escuela de Ciencias Exactas y Naturales de la UNED, el Colegio de Profesionales en Informática y Computación, la Comisión de Telecomunicaciones y la Sociedad de Comunicación IEE Consoc. Extiendo un cordial saludo a las autoridades de gobierno que nos acompañan, estudiantes, tutores, invitados especiales y público en general. Así que sean todos bienvenidos. Seguidamente, las palabras de bienvenida a cargo del señor Esteban Chanto Sánchez, administrador de laboratorios remotos y virtuales de la carrera de Ingeniería en Telecomunicaciones.
Hola, ¿qué tal? Buenos días. La Comisión de Telecomunicaciones del Colegio de Profesionales en Informática y Computación, CEPIC, la Sociedad de Comunicaciones de Costa Rica, CONSOC, y el programa de Ingeniería de Telecomunicaciones de la Universidad a la Distancia, les queremos dar la más cordial bienvenida a este ciclo de charlas que inicia hoy sábado 15 y se extenderá toda la semana hasta el 20 de mayo, dentro del marco del Día Internacional de las Comunicaciones a celebrarse el próximo lunes 17. Pero aquí nosotros desde hoy iniciamos. Como universidad nos interesa construir y formar criterio en temas que son de interés nacional y entre todos podamos aprender y lograr construir nuevos conocimientos. Sin más por el momento, demos por iniciada esta jornada de charlas y espero que sean de agrado de todos ustedes. Gracias.
Gracias, señor Chanto. A continuación, la primera conferencia con el tema el estándar IEEE 802.11b, redes inalámbricas extremadamente de alto tráfico, a cargo del señor Giovanni Geraci. El señor Geraci es profesor de la Universidad de Pompeu, Fabra, en Barcelona, y coordinador de Ingeniería en Telecomunicaciones, miembro de la IEEE, editor de IEEE Transactions of Wireless Communications and IEEE Communications Letters, and the Wireless Communications Symposium co-chair for IEEE y CC22 co-editor del libro UAV Communications for 5G and Beyond. Ha sido galardonado en la Caixa Junior Leader y también en Ramon y Cajal. Así que, sin más preámbulo, el señor Geraci.
Hola, buenos días, buenas tardes aquí en Barcelona. Es un placer participar en este gran evento. Mi presentación será en inglés, porque pues el inglés es el idioma de lo que voy a hablar. Voy a compartir mi pantalla y por favor me avisáis si podéis verla.
Sí.
Vale, pues voy a cambiar al inglés ahora, pero claro, si hay algunas preguntas en castellano no hay ningún problema. Okay, so hi everyone. It's a great pleasure to take part in this event. I'm really honored to be even the first one opening this week dedicated to telecommunications from a country that I very much like, Costa Rica, although I have never been there, but I have heard great things about the country and its people. So today I will talk about something that we are all very familiar with, which is Wi-Fi. Probably some of you in the audience are not technical experts in this field, but I'm sure that all of us have used Wi-Fi at some point, and we all know why Wi-Fi is important. The title of my talk is IEEE 802.11be. This is the technical name of the standard, let's say the protocol, that will become Wi-Fi 7. So right now, the latest technology we're using is Wi-Fi 6, and it has some technical name. But in 2024 or 2025, there will be a new generation, and all the engineers and the standard, they are working on this new generation of Wi-Fi, okay, which will be Wi-Fi 7 in about 4 years' time from now, okay? So let me just introduce myself very briefly, although I've received a very nice introduction already. So I'm Gio. I'm based in Barcelona at University Pompeu Fabra. Before that, I lived in many countries, about 10 countries all over the world. But now I'm very happy in Barcelona. I used to work in the industry for Nokia Bell Labs, and I got my PhD in Australia. The university where I work is a really nice place, in my opinion. It has been ranked among the top 10 young universities in the world, according to Times Higher Education. If you know anybody who's interested in working with us to do research on 6G wireless communications, please get in touch, and hopefully we can have opportunities to collaborate. So today I will talk about Wi-Fi, but I also do research in other domains, and in particular, I'm interested in communications for drones, aerial communications, satellites, etc. So now let's keep going. Let me say thanks to some great colleagues that have contributed to some of the work I will present today. Adrian from Huawei in Paris, Lorenzo from Nokia in Stuttgart, David from Huawei in Paris, and Boris from UPF here in Barcelona, and the funding that has supported me. Right, so this is the outline of the talk today. As you can imagine, Wi-Fi is a really big topic, okay? And there's really not enough time to say everything, and probably not enough expertise even. I guess none of us knows everything about Wi-Fi, okay? So I'll try to give a high-level view. This presentation is technical, I'm afraid, but I'll try to make it as simple as I can. So here's the structure. I will introduce Wi-Fi, okay? I will tell you a little bit about why we are interested in improving Wi-Fi, okay? And then I will talk about some upgrades that will come in Wi-Fi 7 compared to the current standard, which is called 11AX, okay? So the new standard is called 11BE, as you see in the title of my presentation. The old standard or the current standard is called 11AX, okay? Then I will talk about some other feature in 11BE that are not just incremental, but you will see they're really disruptive. They are a paradigm change compared to 11AX. So I prefer to classify all the new features into two groups. Some of them are upgrades and others are completely new features, okay? And then I will show you some performance results to highlight the value of this new standard, how it can improve things compared to the current Wi-Fi. So let's get started. Wi-Fi really doesn't need an introduction. I mean, usually we explain how important Wi-Fi is, but without Wi-Fi, we wouldn't be here right now. I wouldn't be speaking to you, okay? So, and we know that in certain situations, Wi-Fi is key for healthcare, for education, for being in touch with your family, for keeping your business running. So really, I would just skip this slide because we all agree on the importance of Wi-Fi, and we know that there are more Wi-Fi devices in the world than people, actually twice as many roughly. Wi-Fi started its journey around 1997, okay? And there have been different versions, as I anticipated, okay? Many evolutions of Wi-Fi. Sometimes we don't even know, we use Wi-Fi, but we don't know the version of Wi-Fi. But it's something like 3G, 4G, 5G, okay? It evolves, there are different generations. So something similar occurs with Wi-Fi. And today I will talk about the next generation, Wi-Fi 7. So here, this plot shows you how the data rate, the performance, the throughput has been increasing with the new versions, okay? And this has been achieved with some technical improvements by using more and more spectrum. So by using more channels, you get a higher throughput. Notice that this scale is logarithmic. So this improvement is really huge, okay? Then by using MIMO, which is spatial multiplexing, basically sending more than one message at the same time, okay? Then doing multi-user MIMO, meaning serving more than one user at the same time, and some other improvements that I will explain in greater detail later, okay? So the next version of the protocol. The technical name is 11BE, okay, and the commercial name that will be given to this is Wi-Fi 7, okay, just for the ease of remembering it. So this is the focus of this talk. Right. What are the objectives of this new standard? Well, the name of the standard is extremely high throughput, okay? So one of the objectives, of course, is higher throughput. We all want faster internet, okay? And there will be new operations defined, okay? New frequency bands will be open for this, but this is not the only objective, okay? Also, another objective is to improve the latency, the delay, okay? And the jitter, meaning how reliable it is when I transmit data. This is very important because certain applications don't need a high data rate, but they need reliability and they need a very short delay, okay? Because otherwise they just don't work, you know, they work in real time. Think about video, or think about if you want to do remote surgery, just to give an example, you need super short delay, okay? Right. So here's the timeline of the standardization. This figure is taken from my latest paper. So what I want to say here is that the work on the new standard started about 2 years ago, okay? It will hopefully be concluded in 2024, and then we start have products after that, okay? There are two main entities that work on this. The IEEE 802.11 working group, they define the protocols, okay? All the new features, which I will explain today. And then after their job is done, the Wi-Fi Alliance is another entity that gives the approval, the seal, gives that famous black and white logo that we all know for Wi-Fi. So it certifies the products. Basically, it says, yes, this product complies to the standard defined by the IEEE. This other product doesn't. Right. So in this presentation, I will talk about 8 new features that will be in Wi-Fi 7. So these are very technical things. I'll try to keep them as simple as I can, given that probably different people in the audience have different background. But as I said, I divided these new features into 2 groups. The first group are some upgrades from the current standard, meaning the same as it is now, but more, okay? And the other 4 are disruptive new features. It means something that we currently don't have in Wi-Fi, something a little bit revolutionary that hopefully will improve performance a lot. It's harder to work on these disruptive features. Of course, they require more work, but the potential gains could be higher. So let's get started from these key upgrades. So the first upgrade is the use of a wider band. So if you know about telecommunications, you know that the more band you have, the more data you can transmit. So how does Wi-Fi traditionally work? It's been always working, well, on 2 frequencies only. Okay, at the beginning, it was working only on 2.4 gigahertz, but we're talking about 20 years ago, okay? Right now, it works on 2.4 and 5 gigahertz. You probably know this. You sometimes have 2 networks at home because they're on these 2 frequencies, okay? The 2.4 gigahertz has a bunch of channels, but not so many. The 5 gigahertz band is broader. It has more channels. But now a new band in the 6 gigahertz range of spectrum is being opened by several countries for Wi-Fi. This is not defined yet, but for example, the FCC in the US has already opened this. I'm aware of some countries that did this early as well. I think the UK, South Korea, but many more are following, I'm sure, okay, all around the world. So there are new opportunities to use more and more channels in this new band with what's called channel bonding. Okay, I will explain what that is. So what's channel bonding? Channel bonding means that the baseline for a device is to use a certain channel, okay, a certain bandwidth. But then if the one next to it is free, nobody is using it, then you can use a larger one. And then if the other one adjacent is also free, then you can use a further larger channel, okay? So this increases performance a lot. Of course, this is possible only when the adjacent channels are free. And that is not always the case. So this is something that limits how often you can do this channel bonding, okay? So to improve this, in the current Wi-Fi, not in the new one, a feature called Bramble Puncturing was introduced. What does that mean? That I want to do channel bonding. It means I want to use not just my primary channel, but more channels also. I want more and more slices of the cake. But then the adjacent channel is occupied, for example, because there are other devices that are using Wi-Fi in the same area. So what I do is basically I don't transmit in this one that is occupied in the white one, but I still bond the adjacent ones. So this is called Bramble Puncturing. Basically, it means that I do not transmit anything in this frequency range. Okay, I puncture the preamble and I still use the band. So this is of course more efficient, because without this you would only use 20 megahertz, but with this approach you end up using 60 megahertz. Okay, so it's a rather simple concept after all. So in the new Wi-Fi 7 or 11BE, basically the same thing is going to be extended. So right now there's a limit that you can put together up to 160 megahertz. In 11BE, you'll be able to put together up to 320 megahertz. Okay, why this is being designed? Because as I say, there's a new bandwidth that we'll be able to use, and this gives a lot of space. There's over 1 gigahertz available in principle. Okay. So this is probably going to be very useful. And notice that only the new devices, the new generation of devices, the Wi-Fi 7 devices will be able to use this band. So it will be also less competitive. It will be less crowded. So this will probably boost the performance. Right. Let me move on for the sake of time, because we have a lot of things to talk about. So the next thing I want to mention is the introduction of multiple resource units per station. What does this mean? A station is a user in Wi-Fi. It could be your phone, it could be my laptop. Okay, it's a station, anything connected to Wi-Fi. And the allocation of resource units means how many channels and what channels you give in to each of these stations. Okay, and in 11BE, multiple channels can be given, whereas in 11AX only a single channel can be given, and this has some implications. So to explain this, which is rather involved, I need to first explain the concept of OFDMA. So OFDMA stands for orthogonal frequency division multiple access. What does this mean? So the baseline approach for Wi-Fi is the following. How does Wi-Fi work? It's like when we are in a room at a party with people and we all want to talk, but we are polite. So if somebody's talking, I do not talk. I listen, I wait. When I feel that they're finished, then I try to talk. Okay, and if somebody tries at the same time, there's a collision, and again we both shut up, and then we wait a little bit and we try again. So Wi-Fi is very similar. Okay, so look at this. There's some uplink data from a certain station. Okay, and then the access point responds and says, yes, I received your data. It's a downlink block acknowledgement, and then the other station is waiting for a contention time, and then finally the other station also transmits, station 2. Okay. And then access point responds with block acknowledgement and says, yeah, I received you. Okay, this is the non-OFDMA approach, because they only talk one at a time. In OFDMA, what they do is they talk simultaneously, but they share the frequency. Okay, so in this plot, you have frequency versus time. So now they're talking at the same time, station 1 and station 2, but they get half the bandwidth each. And it is the access point that coordinates, that tells them, okay, now you two both, you can transmit at the same time, but you use this frequency, you use this other frequency. So that is in a nutshell how OFDMA works. And there's a limitation. The limitation is that when you put channels together, like I told you before, this blue channel was free, okay? This one is occupied, and these two would be free. Imagine if you have only one station, only one user. Well, you want to give everything available to that user, but you cannot, because you need to give two chunks, this chunk and that chunk, two resource units, and this is simply not possible in the current standard. It's a limitation. So in the new standard 11B, it will be possible to give two separate chunks, okay, two resource units, and then you will solve the problem in the previous slide. So in the previous slide, the user was only getting 20 megahertz, and these red ones were wasted, but now you can give 60 megahertz. So improve transmissions. I can give you more examples of cases where this is really helpful, but for the sake of time, I think this will be sufficient. So let's move on. Spatial streams. So what does this mean? So far, I have talked to you about time resources, frequency resources, okay, but there's another dimension in wireless communications, which is space. So what does that mean? Spatial multiplexing is a very important concept. It consists in sending multiple messages at the same time. It's something like I talk to two people in the room, at the same time, but I convey my voice to one angle such that the station 1 hears me and station 2 doesn't hear me. And at the same time, I speak to station 2 to the other angle of the room such that station 1 doesn't hear me. Okay, so everybody's happy. They are served simultaneously and there's no interference between each other. Okay, so how to do this in practice is to use multiple antennas, because when you have multiple antennas, you can do this thing of directing your transmissions to a specific direction, okay, so to a specific user. So this is the baseline, I would say, for spatial multiplexing, and you can do this in downlink and in uplink, in both directions, okay. So at the beginning, it was introduced only for downlink. Then in 11AX, the current standard, is also introduced in uplink. Okay, and how does it work? When you do it in uplink, all these users that are transmitting to you at the same time, they need to coordinate because you want to receive all their messages aligned. Otherwise, it's very messy and you cannot separate them. Okay, so there's a trigger frame sent by the access point, and then all of them know when they have to start transmit, with what power, etc., and when they have to stop. And then the access point sends an acknowledgement. So this is already in place. What is being done for the next version of Wi-Fi is increasing the number of devices that can actually do this. Right now, the limit is for 8, okay? And this will be increased to 16 in 11B. So basically twice as much the current capability, but this has technical issues. So that is the reason why I included in this presentation. Why? Because imagine that you want to send messages to 2 different users. You need to know where they are. So they first need to tell you where they are. So how does this telling you where they are work? It's what we call channel state information acquisition. So basically estimating where the user is. And how is this done? Well, the current approach works like this. The access point says, hey, where are you guys? And then each one responds and says, I'm here, I'm here, I'm here. They do it one at a time. Okay, so of course, the more of them, the more time it takes because they do it sequentially. So this doesn't scale. When you want 16 of them to do this, the overhead is just not acceptable. It makes it not worth it. So a different scheme is being introduced, okay, based not on explicit feedback, but on implicit feedback. It means that basically directly the users simultaneously all send some reference signals to the access point, and this way the access point is able to estimate the channel. Okay, so not sequentially, but all at once. This is a potential approach. It's not finalized yet, but this is probably the idea that is going to be pursued. Okay, and then the last feature I'll talk about for this first part is a new modulation scheme for PQAM. So what does this mean? This is a constellation. So in digital communications, you use constellations. It means there's a different number of symbols that the transmitter sends to the receiver, and the receiver decodes the corresponding symbol. The bigger this constellation, the more information carried by each symbol that I transmit, okay? But the gain is logarithmic, okay? So it's not that if you double the size, then you double the information. Then you gain a logarithmic logarithm of 2, okay? So long story short, in Wi-Fi, in the current version of Wi-Fi, the size of this constellation is up to 1024 symbols. And in the next version of Wi-Fi, it will be up to 4096. Okay, so it will be huge. Of course, this means that you could potentially send one symbol and carry a lot of information with that symbol, but this only works when you have very, very good channel propagation conditions, when you have a very good signal to noise ratio. Okay, and this typically is not easy to achieve. You can achieve it under specific circumstances that I have listed here, and that for the sake of time, perhaps I cannot describe, but basically you can use beamforming, directing your transmission such that it's received very strongly by your receiver, and then you create very good conditions for that. And there's some other requirements, okay? But this is the basic idea that I wanted to convey. Now, I hope I'm doing good with time. I'll move on to the second part. So I already talked about 4 features so far. And now, which, as you saw, they were upgrades, something that was already there, but now it's going to be more, okay? But these next 4 features I will talk about, they are really new, disruptive, paradigm shifts compared to current Wi-Fi. So they're really promising in terms of performance and what they will enable Wi-Fi to do. So, not just searching your email. Okay, so the first one is HARQ, which means hybrid automatic repeat request. So how does it work right now in Wi-Fi? Imagine that the access point transmits a message and the station doesn't receive it, for example. Then the access point will retransmit the message. The one that is not received or it's received with errors is discarded, okay? The new message this time is correctly decoded. So good. This is called automatic repeat request. So when I don't receive, there's a repetition. Cool. We could do better. How? With what's called hybrid ARQ, hybrid automatic repeat request. So actually cellular systems like 4G, 5G, they already use this. Wi-Fi doesn't use it because, Wi-Fi has to be simpler. A Wi-Fi router, how much does it cost? I don't know, but it costs much less than a 4G base station, probably 100 times less, okay? So, but now that they think that the time is mature to introduce this in Wi-Fi. So what does that mean? That the access point transmits a certain packet, and if this packet is corrupted, it's not received, the station doesn't throw it away. It keeps it, and it just tells the access point, that was not good. The access point repeats, and then this packet is also not good, but when you put it together to the previous one, these 2 corrupted packets make up for a good one, okay? So the station is able to transmit. So of course, this has robustness, okay? Against collisions, against noise, against interference, okay? Of course, it adds complications because you need to buffer all these packets that you keep receiving and then combining them. So one should study effectively, what the gain is in real scenarios. Is it worth it or not, and when? Next feature is called multi-link operation. This is quite interesting. It's one of the star features of the new Wi-Fi 11B. So multi-link operation means operating in multiple links, obviously. So do you remember that I told you that there are going to be probably 3 bandwidths in the next Wi-Fi, okay? So one could operate on a single link, okay, on a single band, okay, at a time. But wouldn't it be better to have a huge brain that knows how to use all of them at the same time? Of course, it would, right? And there are many things that we can do if we simultaneously use these 3 bands. Here's some examples. We could do load balancing. So depending on the traffic conditions, we use one or the other. We could aggregate data, meaning that we use both of them at the same time to send data faster. We could do transmission and reception in different bands. I transmit here and I receive here at the same time, for example, okay? And we could separate control and data plane. What does that mean? In one band, for example, I send my data, and then in the lower band, I send and receive control information, for example, for the access point, okay? This is just examples, but it's an area of research that is really worth exploring, that I think is very interesting. Here I'm going to give like a toy example, just to clarify it, because maybe it's not clear enough. So imagine that you have downlink and uplink transmission between access point and station, okay? And you have 2 bands, 5 gigahertz and 6 gigahertz, just 2, for example, okay? You could have 3. And here, I show you when the packets arrive, okay? And what I do on each of the 2 bands. So gray means that the channel is busy. Yellow means that I'm doing downlink transmission, and blue that I'm doing uplink transmission. So just simple example, follow me. The packet number 1 arrives in downlink. Because the 5 gigahertz band is occupied, I use the 6 gigahertz band. So I'm doing opportunistic link selection, okay? Then another packet arrives in downlink. Now both of them are free. So I use both of them at the same time by doing link aggregation, and I transmit faster because I'm using both, more resources. Then another packet arrives here in uplink this time. The 6 gigahertz band is occupied, so I use the 5 gigahertz. Another downlink packet arrives. I use the 5 gigahertz again because it's free. And at the same time, an uplink packet arrives. So what I do is I do downlink and uplink on two frequencies at the same time with what's called full duplex. Okay, so obviously you can see the potential of multi-link operation, but at the same time, it has to be really well engineered to work appropriately. So let's move on to access point coordination. So, you know, we all have a router at home for Wi-Fi. Okay, that is an access point. Typically, we have only one, and typically this access point does not cooperate with another access point. Okay, they work individually, but coordination could really improve the function. Because remember how Wi-Fi works. It works just like people in a room, they do not talk at the same time. So if they could coordinate, then more people could talk at the same time with better performance. So let's start with what I call, so here you see, I call it low complexity access point coordination. I will explain some simple approach. Then there is advanced access point coordination. So the advanced is more complicated, but the performance is going to be better. So let me go through that. So the first approach I will talk about is called coordinated OFDMA. Basically, it's like two access points, like these ones in the figure. They coordinate in the time domain or frequency domain. In this example, in the frequency domain, okay? So they basically have a cake and they split it. The access point one says, I'll take this side, you take the other bandwidth. So we transmit at the same time, but on different frequencies that we agreed. So we are not interfering to each other, okay? So there is a simple solution, I would say, that it's supposed to help. But of course, each one is only using half of the cake, not the other half. Another approach is called coordinated spatial reuse. So this doesn't work by splitting frequency or time. It works in the power domain. So what does this mean? This is something like, you want to talk at the same time that I'm talking, that's okay, but just go to the other side of the room and don't shout. Just talk quietly. Something like that, okay, just to give you an idea. So here's this figure, take a look. You have access point one transmitting to station one, okay? Access point two transmitting to station two. If they transmit at the same time, then it doesn't work because access point one would interfere to station two and station two would not be able to receive the message from access point two, okay? So there will be a collision because they are not coordinating their transmissions, these two access points. If they coordinate it, what happens? Access point one transmits to station one, but reduces its power. So because it reduces its power, the transmission doesn't reach station two, doesn't disturb station two. So station two is able to hear the message from access point two clearly and decode it. So everybody's happy now, and everybody can transmit at the same time. Of course, they had to reduce their power, right? Which means that probably they have to send data more slowly. Right. Now let's talk about more advanced access point coordination. It's the last feature that I'll introduce, and then I'll show you some performance results. Right. So there are two approaches that I want to describe, okay, introduced for the new Wi-Fi 7. They're still working on this, but hopefully it should be there in 2024. So the first one is called joint transmissions, or DMIMO, distributed MIMO, network MIMO. This technology has many names. Different people have called it differently, okay? How does it work? So you have two access points that have the same coverage area, you know? So if they transmit at the same time, they would collide because they're too close to each other. So how can I do such that they can transmit at the same time? Well, I can have joint transmissions. It means that both access points serve both stations, okay? So both access points transmit to both users. So now there is no more any interference. There's no longer interference. Whatever the access point send is useful signal, it's good signal, okay? But in order to do this, they obviously need to coordinate each other, okay? They need what's called a high-speed backhaul because access point one needs to tell access point two, hey, here's the message that I want to send to station one. Can you also send it at the same time coordinated, okay? And notice that this, for station two to receive it well, it has to be perfectly aligned at the symbol level. So this requires very good synchronization between these two access points. And if you want to do this for more than 2 access points, well, you can imagine the level of coordination increases, okay? Obviously, this is a solution that has the most demanding requirements in terms of synchronization and backhauling, but really it promises huge gains because, you know, you get rid of interference, basically, which is the performance limitation. Right. Then another solution, which is something in between joint transmissions and nothing, okay, is called coordinated beamforming. So this is something that I worked on myself when I was at Nokia Bell Labs. We had some original ideas that then they were developed into this. So I'm particularly fond and happy to talk about this this technology because I feel it partially mine a little bit. So how does this work? Again, we have 2 access points that are overlapping, okay? But now I'm not asking the other access point to also send data to my station. I'm not asking for that. What I'm asking is, please don't interfere to my station, okay? And how is this possible? So what I'm asking is for interference suppression. I'm asking the other access point, you do transmit to your station, but somehow make sure you don't send any interference to the direction of my user, okay? And this is a little bit difficult to explain, but it can actually be obtained in mathematical terms when you do wireless transmissions by placing what's called a radiation knob, okay? By suppressing the interference you generate in a certain direction, okay? So this is mathematically possible when you have multiple antennas. The same way, when you have multiple antennas that you can direct the signal to a direction, you can also suppress the signal to another direction, okay? So if access point 2 is so kind to do this to station 1, and access point 1 is so kind of doing this to station 2, they're very happy because they receive a good signal and they don't receive interference. Everybody can talk at the same time, and this doesn't have the same requirements as the previous scheme. Now, all access point 2 needs to know is where station 1 is, to know where to suppress interference. And likewise, access point 1 needs to know where station 2 is to suppress interference. Okay, so simplified requirements, but very, very good potential. Right. So if you're still with me now, I'm just going to talk about some performance evaluation of this last feature that I described, this one, coordinated beamforming. I will show you the gains. I will show you, like, what do we gain if in the new Wi-Fi we include this new feature. So performance evaluation for coordinated beamforming. So in order to show you that, I need to compare, obviously, to some baseline, okay? And I will compare 3 different scenarios now. The first is a baseline system that doesn't have any spatial reuse coordination, okay? So let's look at the figure. Because there is no coordination at all, access point 1 transmits, access point 2 needs to shut up, and all the stations need to shut up because they might hear each other, okay? So they only can do time sharing. This is the baseline, simple. It's basically how Wi-Fi works. Then we consider another scheme. Now there is some coordination, but it's just in the power domain. So now access point 1 is transmitting, and it tells access point 2, hey, you can still transmit while I transmit, but lower your power. So this is a power-based spatial reuse. Okay, so whenever this is possible, access point 2 will reduce the power and transmit to this, well, this station, let's say, will transmit to access point 2, for example, in uplink, okay, with a reduced power. But others, for example, cannot. Because, for example, this one is closer, it would have to reduce further its voice, and then it wouldn't be enough, for example, to transmit to access point 2, okay? Cool. And then the third scheme, it's the one that we are proposing, this coordinated beamforming. Sorry. This coordinated beamforming. So now, not only these 2 stations can transmit at the same time, these 2 different devices can transmit at the same time if one lowers the power, but the whole process is facilitated because they are placing radiation noise, because they are suppressing interference. Okay, so this suppressing interference allows to speak loudly, if you want me to make an analogy, a metaphor. Okay, so because now this access point suppresses interference, all these devices suppress interference, they can basically talk at the same time without being heard. It's something like, okay, now I'm covering my ear towards your direction, so feel free to speak louder, because now I'm covering my ear, I don't hear you, you know, something, I'm doing some noise canceling, something like that. Okay, just to give the idea. So you can expect that with this approach, everybody can transmit at the same time and more often. They don't need to wait. So remember what I told you, that many applications need low latency, low waiting time. This is going to be an enabler for those applications. So let me show you quantitatively by how much. So I consider this system. There are two different types of traffic, you know. So, you know, many devices use Wi-Fi, smartphones, laptops, any appliance, and the type of traffic, the type of applications is different. So here we considered with my colleagues two types of traffic: uplink broadband traffic, which is a lot of data but irregularly arriving, okay, without particular delay constraints. And then a latency sensitive augmented reality traffic that comes regularly. The traffic is not a lot, but when it comes, it needs to be delivered fast. It cannot wait. Okay, so it's latency sensitive. Cool. So so let me just show you a comparison. Here's the detail of my simulation setup. Basically, the important things is that we consider two access points mounted on the ceiling, okay, and many stations, okay. 16 of them are broadband and 8 of them are low latency. We're gonna look at the latency of these stations to see how happy can we make them, right? And in all of this, the coordinated beamforming scheme that I explained will be implemented, where access points suppress interference towards these low latency stations, such that they can transmit all the time without disturbing anybody, right? As they need. And here is probably the final slide, okay, with the performance. So I'm just going to explain this a little bit. So you see three schemes are compared, the three scenarios that I described. The first one is baseline 11AX, the current Wi-Fi, without any fancy special reuse system, okay? The red one is the current Wi-Fi, but with this power domain coordination, where, hey, if you lower your voice, you can keep talking. And the yellow or orange one is the potential new Wi-Fi with this coordinated beamforming, where I suppress interference and I let people talk at the same time. And here I'm showing you the latency of your packets in milliseconds. And for the latency, I showed the median latency, the 5% worst, the 1% worst, and the 0.01% worst latency. This is very important because it gives you a measure of reliability. It tells you what happens in the worst possible case. So while the baseline Wi-Fi works pretty well, there are still cases where its latency exceeds 200 milliseconds, which is about 1 order of magnitude more of what you can achieve if you implement this coordinated beamforming scheme that was proposed. Okay, so to summarize, the current 11AX Wi-Fi 6 without capabilities has a good latency half the time, but in some cases it exceeds 200 milliseconds. Okay, whereas if we use coordinated beamforming, well, we reduce the worst case latency pretty much by an order of magnitude. The question could be, does this come at a price? You know, we are helping these low latency augmented reality base stations to transmit, stations to transmit more often. Are we penalizing the other stations? Well, the answer, although it's not shown for the sake of time, is no. Okay, this scheme also pretty much preserves the throughput of the broadband stations. Okay, right. So I'm not sure how good I'm doing with time, but basically here are a few references if you're interested in this topic that I recommend going through. And if I have to recommend one in particular, well, it would be number one, because it's the paper that we just published. Basically published in April 2021. This paper is short, 6 or 7 pages. Basically, it best reflects the presentation that I gave today. And it also has received international press coverage in many, many languages, including Spanish. So we are quite proud of it. So if you're interested, do take a look, please. And with this, I have concluded my presentation. So if there are any questions, I'll be very happy to take them.
Ok, en este momento vamos a abrir el espacio de preguntas. Las mismas las pueden hacer por medio de las plataformas en las cuales estamos en vivo y de manera escrita. Vamos a dar alrededor de 2 minutos para todas aquellas personas interesadas en preguntar.
Nos ingresa, Nancy, tal vez una pregunta a través de el WhatsApp que también hemos habilitado, que nos preguntan, vemos que cada día que pasa se hace más necesario que las comunicaciones tengan velocidades simétricas. ¿Es esto posible con el Wi-Fi 6 y con el 802.11be? Esa es la pregunta que pues nos hace don Josué Estrada.
Sí, voy. Pues sí, me parece muy buena pregunta y estoy de acuerdo. De hecho, uno de los puntos que quise comentar, no lo hice por falta de tiempo, es exactamente la diferencia, la distinción entre downlink y uplink. O sea, downlink es una transmisión desde el access point a nuestro dispositivo y el uplink al revés. Y al principio, una de las mejoras que se introducieron en las varias versiones de Wi-Fi fueron introducidas en el downlink only, solo en el downlink. O sea, por ejemplo, el multi-user MIMO, que quiere decir la transmisión a varios usuarios a la vez, fue introducida al principio solo en el downlink. Pero claro, aunque todavía entonces la mayoría del tráfico fuese downlink, el uplink también es necesario, porque habéis visto cómo funciona. Cuando yo recibo un paquete y me llega bien, pues tengo que dar un acknowledgement. Tengo que decir si me ha llegado bien para que se siga la transmisión. Y entonces tener este bottleneck en el uplink me iba a limitar el funcionamiento global de las transmisiones. Y hoy en día, muy buena observación. El tráfico es más y más simétrico. Y hay nuevas aplicaciones incluso donde hay más uplink que downlink. Y entonces yo creo que esas mejoras introducidas, por ejemplo, el multi-user MIMO, ambos en downlink y en uplink, pues ayudan. Y ya eso está en 11AX. Claro, a veces en uplink hay limitaciones porque el uplink lo hacen los dispositivos y a lo mejor son dispositivos más baratos que el access point. Pero, por ejemplo, el Coordinated Beamforming, que es la última feature que he presentado, pues, como habéis visto, eso se supone que mejore la latencia, por ejemplo, en uplink como en downlink. Entonces, sí, creo que vamos en esa dirección.
Muchas gracias. Me indican que tenemos una consulta adicional. Vamos a ver por dónde la podemos canalizar la pregunta.
Nos pregunta a través de las redes, que lo pueden ver en la parte inferior de la pantalla. Nos pregunta Fradian Méndez García, ¿cuándo se implementaría este nuevo protocolo? Me imagino que eso es muy dependiente de los países, Giovanni.
No, la implementación, la estandarización, no sé si se acuerdan, yo he enseñado una de las primeras diapositivas con el time frame, ¿okay? O sea, dónde va el estándar, los varios pasos. Y se supone que todo eso se completa en 2024, ¿vale? Habrá versiones intermedias, varias releases, 4 creo, si no me equivoco, pero en 2024 ese es el target, ese es el objetivo. Claro, luego pueden haber algunos retrasos por COVID, por otras razones, pero yo creo que las empresas, las compañías se pondrán a trabajar para tener productos cuanto antes. Una vez el estándar esté listo, la Wi-Fi Alliance, el estándar lo hace la IEEE. Luego la Wi-Fi Alliance, pues certificará productos que cumplen con el estándar. Y entonces ya en 2025 tendremos algunas cosas. Lo que tengo que decir es que también lo que pasa normalmente, hay productos de first wave, second wave, ¿vale? Es lo mismo que pasa con la 5G. Se vende algo que es 5G, pero a lo mejor tiene algunas características de 5G, pero no todas, ¿vale? Pasará lo mismo. Habrá nuevas características incluidas, pero a partir de 2025 podría decir, pero poco a poco todas las características que he presentado hoy, poco a poco todas entrarán. Eso tardará un poco más, creo. Normalmente sabe, como se puede imaginar, primero se implementan las que cuestan menos, son más fáciles y te dan una ganancia más rápida o que hay exigencia de mercado para esas features, ¿ok? Para aplicaciones específicas. No sé si esto aclara, digamos.
Muchas gracias. Acá tenemos un comentario de Musu Nassim. Dice que muchas gracias por la presentación. Todo muy bien para él. Alexander Vega nos dice excelente presentación. Muchas gracias. Entonces, vamos a ver. Aquí tenemos una pregunta. Dice de Juan Pablo Garrido. ¿Es el Channel Bonding el homólogo de Carrier Aggregation en LTE?
Sí, me parece una muy buena manera de explicarlo, de hecho. Sí, diría que sí. Se trata de, pues, tienes dos canales, dos tubos, pues si los dos están libres, pues úsalos a la vez para poder mandar más datos simultáneamente. Y en Wi-Fi eso se tiene que usar mucho, porque cada canal de 20 MHz es bastante pequeño. Y entonces, cuando sea posible, siempre hay que usar más canales.
Aquí tenemos una última pregunta del Colegio de Ingenieros en Informática. Harry Barrantes nos pregunta, ¿cuáles podrían ser las herramientas más importantes del 802.11pe para competir por el espectro en lugares con alta densidad de equipos, como en torres de oficina con diferentes inquilinos?
Esta pregunta es excelente, si puedo decirlo. Es una pregunta realmente excelente y gracias, Ari, por hacer esa pregunta. ¿Por qué es excelente? Porque cada una de las features que he presentado mejora las prestaciones y el rendimiento, pero en contextos distintos. Y este contexto que menciona Harry es especialmente importante porque sabemos que eso es uno de los problemas de Wi-Fi. Wi-Fi funciona muy bien cuando estamos en casa, pero cuando estamos en el aeropuerto ya deja de funcionar. ¿Por qué? Porque es un espacio muy concurrido, porque hay muchos usuarios. ¿Cómo se puede resolver? Yo diría que la feature del Coordinated Beamforming en la que me he enfocado al final de la presentación y por la cual he presentado las simulaciones y los resultados, creo que esta podría ser la que realmente va a atacar este problema. ¿Por qué? Porque si haces este juego de suprimir la interferencia y dejar que alguien a tu alrededor pueda transmitir al mismo tiempo, pues entonces mejoras lo que ocurre en espacios concurridos, que ya esta densidad extrema ya no te hiere tanto. Entonces sí, eso es lo que opino.
Bueno, nuevamente muchísimas gracias al señor Geraci por formar parte de esta actividad, por dedicarnos este espacio desde Barcelona y le mandamos atentos cariños desde nuestro país.
A vosotros, un placer enorme.